All right, so you wanted to know more about how databases actually store and retrieve information. Get ready for a fascinating trip into the world of storage engines.
Yeah.
We're cracking open Chapter 3 of Designing Data-Intensive Applications, the one that's all about storage and retrieval.
Okay.
And we're going to find out how to pick the perfect storage engine for our needs.
Right.
And trust me, it's going to be a wild ride.
What's fascinating is we can actually start with something super simple.
Okay.
Like, imagine a bash script.
Wait, a bash script?
Yeah.
I use those to automate tasks on my computer,
Right.
not build complex databases.
Well, you can represent a very basic key value store,
Okay.
like a dictionary,
Mm-hmm.
with just two bash functions.
Okay.
One function appends a new key value pair to a file,
Okay.
much like adding a new entry to a dictionary.
I gotcha.
And the second function searches the file for a specific key and returns its value.
So it's like we're building a mini database
Right.
just by adding lines to a text file.
Exactly.
I see how that would be super efficient for writing data.
Yeah.
But finding a specific piece of information in that ever-growing file
Right.
sounds like a nightmare.
That's where the simplicity breaks down.
Okay.
As the file grows, searching by scanning the entire file becomes incredibly slow.
Makes sense.
Real-world databases need a faster way to locate data.
And that's where indexes come in.
Exactly. Indexes are like signposts
Okay.
that point directly to the information you need,
Mhm.
eliminating the need to scan the entire data set.
Indexes, the express lane to data retrieval.
Yeah,
But I'm guessing there's a catch?
you're absolutely right.
There's no such thing as a free lunch,
There's always a trade-off.
especially in software.
The trade-off with indexes is that while they make reading data incredibly fast, they slow down write operations.
Okay.
Every time you add or update data, the index needs to be updated as well,
Gotcha.
adding overhead to the process.
So it's a balancing act?
Yeah,
Faster reads come at the cost of slightly slower writes.
that's the trade-off.
And understanding this trade-off
Right.
helps us,
Helps you, the listener.
helps you, the listener, choose the right database type
Exactly.
and fine-tune its performance for your specific needs.
Precisely.
Now, I know there are different types of indexes.
Yes.
Each with its own strengths and weaknesses. So
Mhm.
where do we even begin?
Let's start with hash indexes.
Okay.
Picture a real-world dictionary.
Okay.
Each word, your key, points directly to its definition,
Mm-hmm.
your value.
Gotcha.
Hash tables stored in memory can make lookups incredibly fast.
Okay, so let's say I'm building a social media app
Okay.
where users need to quickly find all their friends.
Right.
Would a hash index be a good choice here?
That's a great question.
Yeah.
And it highlights one of the limitations of hash indexes.
Okay.
While they excel at finding individual records,
Uh-huh.
they're not efficient for finding ranges of data.
Ah, okay.
Imagine trying to find all the words in a dictionary starting with the letter C. By looking up each C word individually,
Right.
instead of simply going to the C section.
Yeah.
Similarly, a hash index wouldn't be the best choice for finding all users
Okay.
within a certain age range,
Gotcha.
or all transactions between two specific dates.
So hash indexes are speed demons for individual lookups,
Yes.
but they fall short when it comes to range queries.
Right.
What about handling massive data sets?
That's another important consideration.
Okay.
Hash indexes can consume a large amount of memory if you have a vast number of keys.
I see.
This can be a problem if your data set doesn't fit entirely in memory,
Right.
leading to performance issues.
So while hash indexes offer incredible speed for specific lookups, they're not a one-size-fits-all solution.
Not really, no.
What other tools do we have in our database arsenal for scenarios like these?
So that brings us to SS tables and LSM trees,
Okay.
which take a different approach to organizing and retrieving data. Imagine S tables, or sorted string tables, as meticulously organized lists of key value pairs,
Okay.
sorted alphabetically. This sorting allows for efficient merging of files,
Okay.
even those larger than the available memory,
Gosh.
using a method similar to the merge sort algorithm.
Merge sort. Divide and conquer.
Exactly.
But how does sorting a bunch of key value pairs help with searching?
That's where the clever design of S tables shines.
Okay.
They combine a sparse index, which only checks some keys,
Mm-hmm.
with the ability to rapidly scan small blocks of data within those sorted files.
So S-tables are like super efficient dictionaries,
Yeah.
combining a high-level index with rapid scanning of smaller sections.
Exactly.
What about LSM trees? How do they fit into this picture?
LSM trees take this concept a step further.
Okay.
Picture a multi-level structure,
Mm-hmm.
using multiple SS tables, constantly merging and optimizing data in the background.
Okay.
This approach leads to incredibly fast write speeds,
Gotcha.
even when dealing with gigantic data sets.
So, while hash indexes are great for quick lookups but have limitations,
Right.
stables and LSM trees sound like they can handle both large data sets
Yeah.
and fast writes.
Exactly.
Is there a real-world example where this type of structure is used?
Absolutely. A great example is Lucene,
Okay.
the powerful engine behind popular search platforms like Elasticsearch and Solr.
Interesting.
It uses a similar structure for full-text search,
Okay.
where the word you search for is the key,
Uh-huh.
and the list of documents containing that word is the value.
Gotcha.
LSM trees allow these platforms to handle billions of words and documents,
Wow.
providing lightning-fast search results.
That's a fantastic example.
Yeah.
It's amazing to think that the same principles powering database storage
Mhm.
are also used to handle the massive amounts of data behind our everyday searches.
That's right.
It seems like we've uncovered two powerful approaches: hash indexes for speed
Right.
and stables and LSM trees for handling massive data sets and fast writes. But is there a scenario where neither of these would be the best fit?
That's a great question.
Yeah.
It leads us to another major player in the world of databases. B-trees.
Okay, I'm intrigued. Bring on the B trees. All right, so we've explored hash indexes, SS stables, and LSM trees, all clever ways to organize and retrieve data. Now we're stepping into the realm of B trees,
Good.
and I'm curious to see how they stack up against these other methods.
B-trees have been a cornerstone of database systems for decades.
Mm-hmm.
And for good reason, they're known for their reliability and efficiency,
Okay.
especially when dealing with large data sets and complex queries.
Okay, I'm picturing a library
Yeah.
with Dewey Decimal System labels and everything.
Right.
But how does this library analogy translate to storing and retrieving data?
Instead of appending data to a log-like structure, B-trees divide data into fixed-size blocks,
Okay,
much like pages in a book.
gotcha.
These pages are organized in a hierarchical tree structure,
Okay.
with each page containing keys and pointers to child pages. This structure mirrors how data is stored on hard drives,
Interesting.
making B-trees incredibly efficient for disk access.
So instead of searching through a giant log file,
Right.
we're navigating a hierarchical structure,
Yeah,
narrowing down our search with each level.
exactly. Each level of the B-tree acts as a guidepost,
Uh-huh.
leading you closer to the target data.
That makes sense.
And this ensures fast lookups,
Mhm.
regardless of how large the dataset grows.
That's great, but I'm also thinking about reliability.
Okay.
What happens if the system crashes in the middle of an update?
Right.
With a log-based structure,
Yeah.
it seems like you could potentially lose data.
That's a great point, and it highlights one of the strengths of B-trees
Okay.
to ensure data integrity.
Uh-huh.
They employ a mechanism called a write-ahead log,
Okay.
or wall.
Gotcha.
It acts as a safety net,
Mm-hmm.
recording every modification to the B-tree in a separate log file
Okay.
before the changes are applied to the main data structure.
So it's like having a backup copy of every transaction,
Right.
ensuring that even if the system crashes unexpectedly, you
Yeah.
can recover the data and restore the B tree to a consistent state.
Exactly. The wall acts like a detailed journal,
Mm-hmm.
meticulously recording every step,
Cool.
so you can retrace your steps and recover from unexpected events.
Okay, B trees sound like the reliable workhorses of the database world,
Yeah.
capable of handling large data sets,
Mm-hmm.
complex queries,
Right.
and ensuring data integrity.
Absolutely.
But haven't they been around for a while?
They have.
Have there been any optimizations developed over the years?
Absolutely. B-trees have been extensively studied and optimized over the years,
Hmm.
leading to some clever techniques that enhance their efficiency.
Like what?
One optimization involves using a copy-on-write scheme,
Okay.
where instead of modifying pages directly,
Mm-hmm.
a modified copy is created,
Gotcha.
and parent pages are updated to point to this new copy.
Mm-hmm.
This improves concurrency, allowing multiple operations to happen simultaneously without conflicts.
So it's like version control for database pages?
Exactly.
Each modification creates a new version,
Right.
ensuring that other operations aren't affected by the changes in progress.
That's right. This is particularly useful in high concurrency scenarios
Okay.
where multiple users or processes are accessing and modifying the database simultaneously.
Now we've discussed hash indexes,
Right.
SS stables, and LSM trees.
Yeah.
And now B trees.
Mm.
It feels like we have an epic battle brewing between these different approaches,
It's a bit like that, yeah.
each with its own strengths and weaknesses.
Absolutely.
How do we choose the right weapon for the job?
It all depends on your needs.
Okay.
When would you recommend a B tree over the other options? B trees are a solid choice for applications that prioritize consistent read performance
Okay.
and need to handle complex queries, especially those involving range searches or multiple conditions.
Gotcha.
Think of a financial application where you need to quickly retrieve transactions within a specific date range
Okay.
and also filter by amount or account type.
I gotcha.
B trees excel in these scenarios,
Right.
providing predictable performance and reliable results.
So if I'm building an application that demands consistent performance for a variety of queries,
Yeah,
B trees are a safe bet.
I think so.
But what about those write-heavy workloads we discussed earlier,
Okay.
where speed is paramount?
In those cases, LSM trees might be a better fit.
Okay.
They excel at handling a constant stream of writes,
Right.
making them ideal for scenarios like logging sensor data, capturing user activity on a website,
That's right.
or tracking real-time financial market data.
I see.
LSM trees are designed to ingest data quickly and efficiently,
Right.
sacrificing some read performance
Okay.
for exceptional write throughput.
So it's a trade-off.
Yeah.
If my application is write-intensive, like tracking social media interactions
Right.
or handling a flood of sensor data, LSM trees are the speedsters I need.
Mm-hmm.
But if I need consistent read performance for complex queries,
Yeah,
B trees are the reliable workhorses I can count on.
that's right.
It seems like understanding the workload is key to choosing the right storage engine.
Absolutely. It's all about matching the tool to the task.
Now, we've been focusing on primary keys, the main identifiers for our data.
Right.
But what about searching based on other fields, like finding all users with a specific email address
Okay.
or all transactions from a particular store location?
That's where secondary indexes come into play.
Okay.
They provide alternative paths to access data, allowing you to search based on fields other than the primary key.
I see.
Imagine the index at the back of a book,
Okay.
which lists key terms and their corresponding page number.
Gotcha.
Secondary indexes work similarly,
Interesting.
allowing you to quickly locate records based on specific criteria.
So it's like having multiple entry points to our data,
Yes.
making it easier to find what we need, regardless of the search criteria.
That's right.
But how are these secondary indexes implemented? Are they built using the same structures as primary indexes, like B trees or LSM trees?
That's the beauty of it.
Yeah.
Both B trees and log-structured approaches, like LSM trees, can be used for secondary indexes.
Okay.
This provides flexibility in tailoring the database to specific query patterns.
Gotcha.
For example, if you frequently search for users by email address,
Right.
you could create a B tree-based secondary index on the email field, ensuring fast and efficient lookups.
So we can choose the best indexing structure for each secondary index,
Right.
depending on how we expect that data to be accessed.
Exactly.
It's like having a toolbox full of specialized tools,
Yeah.
each designed for a specific purpose.
Exactly.
And we've covered indexes in depth.
Right.
But what about the actual values associated with our keys?
Okay.
Where does the rest of the data reside?
That's a great question. And it brings us to the concept of storing values within our database.
Okay.
There are a couple of main approaches here. One is to store the entire record, including all its fields,
Okay.
directly within the index itself.
All right.
This is called a clustered index.
So with a clustered index, the index not only points to the data,
Yeah,
it actually contains the data itself.
that's right.
That sounds like it would make reads super fast, since everything is right there in the index.
Exactly. Clustered indexes are excellent for scenarios
Okay.
where you frequently retrieve entire records based on the primary key.
Gotcha.
They minimize the number of disk accesses required to fetch the data,
Right.
resulting in faster query response times.
But there must be a trade-off.
Of course.
There's always a trade-off in software design.
What's the downside of using a clustered index? One potential downside is data duplication. If you have multiple secondary indexes on different fields, each referencing the same record,
Yeah.
you could end up with multiple copies of the same data
Right.
stored within different indexes.
Makes sense.
This can lead to increased storage space requirements
Gotcha.
and potential inconsistencies if data is updated in one index but not the others.
So clustered indexes are great for speed,
Right.
but can lead to data duplication.
Yeah.
What's the alternative?
The alternative is to use a non-clustered index.
Okay.
In this approach, the index only stores a reference to the location of the complete record,
Gotcha.
which is typically stored in a separate heap file.
Okay.
The heap file stores data in no particular order,
Mm-hmm.
so retrieving a record requires an extra step.
Okay.
First, you look up the reference in the index,
Mm-hmm.
and then you fetch the actual record from the heap file.
It's like having an index card that tells you where to find a specific book in the library,
Exactly.
rather than having the entire book contained within the index card itself.
That's a great analogy.
You save space,
Right.
but retrieving the book requires an extra step.
That's the trade-off.
Non-clustered indexes are more space efficient,
Yeah.
especially when you have multiple secondary indexes.
Mm-hmm.
However, they can be slightly slower for reads,
Right.
since they require an additional disk access
Yeah.
to fetch the complete record from the heap file. So it's a classic trade-off.
It is.
Speed versus storage space.
Yes.
Clustered indexes prioritize speed, while non-clustered indexes focus on efficiency.
That's right.
Are there any situations where you might want to strike a balance between these two approaches?
Yes. There's a middle ground called a covering index,
Okay.
sometimes referred to as an index with included columns.
Gotcha.
In this approach, the index includes not only the key, but also some additional columns from the actual record.
So it's like having a more informative index card
Right.
that contains not only the book's location,
Yeah.
but also a brief summary or a few key excerpts.
That's a great analogy.
This saves you the trip to the bookshelf.
Right.
If all you need is that additional information.
Exactly. Covering indexes can significantly speed up queries
Okay.
that only need to access a subset of columns,
Gotcha.
eliminating the need to fetch the entire record from the heap file.
Yeah.
They offer a balance between the speed of a clustered index
Mm-hmm.
and the space efficiency of a non-clustered index.
So we have a range of options for storing values,
Right.
from the speed-focused clustered index
Yeah.
to the space-efficient non-clustered index,
Right.
with the versatile covering index striking a balance between the two.
Mm-hmm.
It's all about choosing the right approach,
It is.
based on the specific needs of the application
Yeah.
and the types of queries you anticipate running.
That's right.
Now, what about situations where we need to search based on combinations of multiple columns,
Okay.
like finding all users with a specific first name and last name?
That's a great question.
Yeah.
And it leads us to the concept of multi-column indexes,
Okay.
designed to handle queries that involve multiple fields. A common approach is to use concatenated indexes,
Mm-hmm.
where multiple columns are combined into a single key.
Okay, so instead of having separate indexes for first name and last name,
Right?
we create a single index that combines both fields.
Exactly.
It's like creating an index card that lists both the book's title
Yeah.
and the author's name, allowing you to search based on either criterion.
That's right. Concatenated indexes are efficient for finding specific combinations of values
Uh-huh.
or prefixes.
Okay.
For example, if you want to find all users with the first name John
Mm-hmm.
and the last name starting with S,
Right.
a concatenated index on first name and last name would quickly locate those records.
This sounds like a powerful technique
Oh.
for handling queries that involve multiple fields.
Mm-hmm.
Are there any limitations to concatenated indexes?
One limitation is that they're not as flexible as separate indexes on individual columns. For instance, a concatenated index on first name and last name wouldn't be efficient for finding all users with a specific last name,
Okay.
regardless of their first name.
Gotcha.
In those cases, you'd still need a separate index on last name for efficient retrieval.
So concatenated indexes are great for specific combinations or prefixes,
There you are.
but they might not be the best fit for all multi-column queries.
That's right.
What about situations where we need to go beyond exact matches,
Okay.
like searching for similar keys or misspelled words?
That's where specialized techniques like full-text search engines and fuzzy indexes come into play.
Interesting.
These methods utilize a variety of sophisticated algorithms
Okay.
to handle the nuances of human language,
Uh-huh.
allowing you to search for similar words,
Mm-hmm.
typos, misspellings,
Right.
and even synonyms.
It's like having a super intelligent search bar
Yeah.
that understands the intent behind your query,
Right.
even if you make a few mistakes.
Exactly. Full-text search engines like Lucene, which powers Elasticsearch and Solr, use techniques like stemming.
Synonym expansion
Gotcha.
and edit distance calculations
Mm-hmm.
to find relevant results,
Right.
even if the search terms aren't exact matches.
That's incredible.
Yeah.
It's like having a team of librarians
Right.
who not only know where everything is,
Mm-hmm.
but also understand the subtle nuances of language
Yeah,
and can help you find what you need,
exactly.
even if you don't know exactly how to ask for it.
That's a great way to put it.
These specialized techniques make search incredibly robust and flexible,
They do.
allowing us to navigate vast amounts of data
Right.
and uncover insights that might otherwise remain hidden.
Absolutely.
We've covered a lot of ground in our exploration of indexing and data retrieval.
You have?
We've journeyed from the simplest key-value stores
Mm-hmm.
to the sophisticated structures that power modern databases.
That's right.
And we've seen how different workloads and query patterns demand different approaches.
Yes.
Where do we go from here? Now that we've delved into the intricacies of how databases store and retrieve individual pieces of information,
Okay.
let's zoom out and look at the bigger picture.
Okay.
We'll explore how databases are designed to handle different types of workloads,
Right.
from the rapid-fire transactions of online systems
Mm-hmm.
to the complex analytical queries that drive business insights.
Okay, I'm ready to level up my understanding.
Right.
What are these different workloads?
Let's start by contrasting two fundamental types of workloads.
Okay.
Online transaction processing, or OLTP,
Gotcha.
and online analytical processing, or OLAP.
Okay.
OLTP systems are designed to handle a high volume of short,
Mm-hmm.
fast transactions,
Okay.
typically from user-facing applications.
Gotcha.
Think of online banking,
Mm.
commerce websites,
Right.
or booking a ride-sharing service.
Okay.
These systems need to process a constant stream of small updates and retrievals
Right.
with minimal latency,
Gotcha.
ensuring a smooth and responsive user experience.
So OLTP is all about speed and efficiency,
It is.
handling a constant flurry of transactions like a well-oiled machine.
Exactly.
What about OLE?
OLA systems, on
Mhm.
the other hand,
Yeah.
are designed for complex analytical queries
Okay.
that often involve scanning and aggregating massive amounts of data.
Gotcha.
This is the realm of business intelligence,
Mm-hmm.
data warehousing,
Yeah.
and data mining.
Right.
Analysts use OLP systems to uncover trends,
Mm-hmm.
identify patterns,
Okay.
and gain insights from historical data
Right.
to make informed business decisions.
So while OLTP is like the cashier at a busy store,
Yeah.
processing transactions as quickly as possible,
You could-
OLP is like the accountant in the back office,
Right.
meticulously analyzing financial records to understand the bigger picture.
That's a great analogy.
They both deal with data,
Yeah.
but their purpose design
Right.
and the way they handle data are quite different.
Absolutely. For example, an OLTP system might be optimized for quickly inserting dating
Yeah.
and retrieving individual customer records,
Right.
while an OLAP system might be designed to efficiently scan and aggregate millions of sales transactions
Okay.
to generate reports on sales trends over time.
So understanding the type of workload is crucial
It is.
for choosing the right database technology
Hmm.
and designing the system for optimal performance.
Exactly.
It's like choosing the right vehicle for a journey.
Okay.
If you're navigating a bustling city,
Yeah.
a nimble scooter might be the best choice.
Right.
But if you're embarking on a cross-country road trip,
Mm-hmm.
a spacious and comfortable car would be more suitable.
Exactly. The design of a database,
Okay.
including the storage engines and indexing structures we've discussed,
Right.
is heavily influenced by the types of workloads it's intended to handle.
Now let's delve into the world of data warehousing,
Okay.
a specialized area within OLAP where organizations store and analyze vast amounts of historical data
Yeah,
to gain business insights.
exactly.
Okay, I'm ready to explore the world of data warehouses.
Right.
What makes them different from traditional OLTP databases?
Data warehouses are specifically designed for analytical queries
Okay.
that often involve complex joins,
Mm-hmm.
aggregations,
Gotcha.
and filtering across massive data sets.
Okay.
They act as central repositories for historical data,
Right.
often aggregated from multiple sources,
Mm-hmm.
providing a consolidated view for analysis and reporting.
So it's like having a giant library
Yeah.
where all the historical records of a company are meticulously organized and categorized. They're
Exactly.
ready for exploration and analysis.
Data warehouses are designed for exploration and discovery,
Right.
allowing analysts to slice and dice data in countless ways
Okay.
to uncover insights that might not be apparent from individual transactional systems.
But how does the data get into the data warehouse in the first place?
Okay.
It seems like a daunting task
It can be.
to gather and organize data from multiple sources.
That's where a process called ETL comes in.
ETL.
Extract, transform, load.
Okay.
It involves extracting data from various source systems,
Mm-hmm.
transforming it into a consistent and unified format suitable for analysis,
Okay.
and then loading it into the data warehouse.
So it's like gathering raw ingredients from different farms,
Yeah.
processing and refining them into finished products,
Right.
and then stocking those products in a massive warehouse ready for distribution.
Exactly. ETL is a crucial part of data warehousing,
Gotcha.
ensuring that data is cleansed, standardized, and organized for efficient analysis.
Now let's explore how data is organized within a data warehouse.
Okay.
Using specialized schema designs.
Right.
Schema designs.
Yeah.
Are those like blueprints for organizing data within the warehouse?
You got it. Two common schema designs used in data warehousing
Okay.
are the star schema and the snowflake schema. The star schema is named for its visual resemblance to a star,
Okay.
with a central fact table surrounded by dimension tables.
Okay, I'm picturing a star in the night sky.
Yeah.
With the central fact table as the brightest star
Right.
and the dimension tables as surrounding stars, each contributing to the overall constellation.
That's a great visual.
The fact table contains the core measurements or events we want to analyze,
Right.
like sales transactions or website visits.
Exactly.
The dimension tables provide context about those facts, such as the date of the transaction, the product sold,
Right.
the customer who made the purchase, or the location of the website visit.
That's right.
So the fact table tells us what happened,
Yeah.
while the dimension tables provide the who, what, where, when, and why of those events.
Exactly.
It's like having a detailed log of all the company's activities
Right.
with additional information to understand the context of each event.
That's right.
What about the snowflake schema?
The snowflake schema is similar to the star schema,
Okay.
but takes normalization a step further.
Okay.
Dimensions are broken down into subdimensions
Gotcha.
to create a more granular and structured approach.
Okay.
For example, a customer dimension might be further divided into subdimensions for location, demographics,
Gotcha.
and purchase history.
So it's like taking those surrounding stars in our constellation
Yeah.
and using a telescope to zoom in and reveal even more detail, breaking them down into smaller, more specific clusters.
Precisely. While this normalization can offer advantages in terms of data integrity and consistency,
Okay.
it can also make queries more complex.
Right.
Star schemas are often preferred for their simplicity and ease of use for analysts
Gotcha.
who need to quickly access and analyze data.
So star schemas prioritize usability,
Yeah,
while snowflake schemas focus on normalization and granularity.
that's right.
It's like choosing between a simplified map for quick navigation and a detailed topographical map for in-depth analysis.
That's a great way to put it.
Now, we've talked about data warehouses,
Right.
schemas,
Yeah.
and different types of workloads.
Mm-hmm.
Let's circle back to a topic we discussed earlier, column-oriented storage.
Okay.
Remember how this approach flips the traditional row-oriented storage on its head?
I do.
Instead of storing all the data for a single row together,
Yeah.
column-oriented storage organizes data by column,
Right.
keeping all the values for a specific column together.
Exactly.
It's like having separate filing cabinets for each attribute, instead of keeping all the information for a single person in one folder.
Right.
But how does this benefit analytical workloads and data warehouses?
That's a great question.
Yeah.
And it leads us into the exciting world of how column-oriented storage revolutionizes analytical queries. Think about the typical analytical query in a data warehouse.
Okay.
You're often interested in specific metrics across a vast number of records, but you only need a few columns to answer your question.
Right.
For example, you might want to calculate the average sales for a particular product category over the last year.
Okay.
In this scenario, you need the sales and product category columns,
Right.
but you don't care about the customer details, payment methods, or shipping information.
So with a traditional row-oriented database,
Yeah.
we'd have to read through all those extra columns we don't need,
Right.
even though they're irrelevant to our analysis.
Exactly.
That seems incredibly inefficient,
It is.
especially when dealing with millions or even billions of rows.
That's where column-oriented storage shines.
Okay.
By storing data by column, it allows analytical queries to read only the necessary data from disk,
Right.
skipping over the irrelevant columns.
Gotcha.
This dramatically reduces the amount of data that needs to be read,
Okay.
resulting in significantly faster query performance.
It's like having a library where you can request specific chapters from multiple books. Instead of having to check out the entire collection,
Exactly.
you save time and effort by focusing only on the information you need.
And there's another benefit to this columnar approach.
Okay, what's that?
Compression.
Okay.
Since data within a column often has similar characteristics and repeating patterns, column-oriented storage can achieve much better compression ratios compared to row-oriented storage.
So not only do we reduce the amount of data that needs to be read,
Yeah,
we also shrink the data footprint on disk,
exactly.
making those massive analytical queries even faster.
That's right.
Are there any particular compression techniques that work particularly well in this context?
One technique that's especially effective in data warehouses is bitmap encoding.
Okay.
It's particularly well suited for columns with a relatively small number of distinct values,
Right.
which is often the case in data warehouses.
Okay.
Think of a column like gender or country. Instead of storing the actual text values repeatedly,
Yeah.
we could represent each distinct value with a bitmap.
A bitmap.
Yeah.
That sounds a bit technical.
It's pretty straightforward.
How does that help with compression?
Imagine a bitmap as a string of bits,
Okay.
with one bit representing each row in the table.
Gotcha.
If a row has a particular value,
Mm-hmm.
the corresponding bit is set to 1, otherwise it's set to 0.
Right.
For example, in a gender column with values male and female,
Okay.
we'd have 2 bitmaps.
Gotcha.
The male bitmap would have 1s in positions corresponding to rows with male values,
Okay.
and the female bitmap would have 1s for rows with female values.
Makes sense.
These bitmaps can be compressed incredibly efficiently,
Okay.
especially if they're sparse, meaning they have a lot of veers.
So instead of storing male or female repeatedly,
Right.
we're essentially using these compact bitmaps as a code to represent those values.
Exactly.
That's a really clever way to reduce storage space.
Bitmap encoding is incredibly powerful for compressing data in data warehouses,
Right.
where many columns have a limited number of distinct values.
Now, we've talked about sorting for log-structured indexes,
Right.
ensuring that data is organized for efficient retrieval.
Yeah.
Does sorting play a role in column-oriented storage as well?
It does.
It seems like if data is stored by column,
Yeah.
the order of the rows wouldn't matter as much.
You're right that the order of rows within a column might not seem crucial at first glance.
Okay.
But sorting actually plays a vital role in optimizing query performance,
Interesting.
even in column-oriented storage.
Okay.
Even though data is stored column by column,
Right.
we can sort the entire table based on one or more columns.
Mm-hmm.
This creates an implicit index within the columnar structure.
So even though the data is physically stored by column,
Right.
we maintain a logical order based on certain key columns.
Exactly.
Like having a multi-level sorting system within our filing cabinets,
Yeah.
making it easier to find related documents quickly.
This sort order makes queries that target specific ranges incredibly efficient. For example, if you frequently analyze sales data for a specific date range, sorting the table by the date column would allow the database to quickly pinpoint the relevant data blocks
Right.
without scanning through unnecessary data.
So we can have our cake and eat it too.
We can.
We get the benefits of columnar storage for efficient data access.
Yeah.
And the advantages of sorting for optimized range queries.
Exactly.
Now, what about updates?
Okay.
If we can't simply overwrite data in a compressed column,
Yeah.
how do we handle changes in a column-oriented database?
You're right. Updates pose a challenge for column-oriented storage,
Yeah.
especially with compression techniques like bitmap encoding.
Right.
But remember our friend the LSM tree.
Ah, the LSM tree.
Yeah.
Our superhero for handling write-intensive workloads.
Exactly.
How does it come into play here?
LSM trees, with their in-memory buffering and background merging process, are perfectly suited for handling updates in a column-oriented database, instead of directly modifying compressed data on disk.
Right.
Updates are first buffered in memory.
Okay.
Then periodically, these updates are merged with the on-disk data
Gotcha.
in a sorted and optimized manner.
So it's like having a staging area
Yeah,
where changes are collected and then integrated into the main database periodically.
exactly.
This ensures that updates are handled efficiently
Yeah.
without constantly disrupting the compressed and sorted structure of the columnar storage.
That's right.
It's like having a team of librarians who meticulously organize and reshelve books overnight,
Yeah,
ensuring that the library is always in tip-top shape for the next day's visitors.
that's an excellent analogy.
LSM trees allow column-oriented databases to achieve both high write throughput and efficient read performance.
That's right.
Making them suitable for a wide range of applications,
Right.
including data warehousing.
Absolutely.
So we've seen how column-oriented storage is a game changer for analytical workloads,
It is.
allowing us to efficiently access and analyze massive data sets But what about situations where we need answers instantly?
Okay.
Analytical queries can sometimes take a while to run,
I can.
especially when dealing with large data sets.
Right.
Are there any ways to speed up these queries even further?
That's a great question.
Yeah.
And it leads us to the world of pre-computed insights,
Okay.
where we leverage techniques like data cubes and materialized views
Mm-hmm.
to speed up query response times.
Right.
Imagine you're an analyst who frequently runs queries to calculate the total sales for each product category by month.
Okay.
Instead of running this query from scratch every time,
Yeah.
you could pre-compute these aggregates
Gotcha.
and store them in a separate structure called a data cube.
So it's like having a summary table that's already calculated and ready to go,
Right.
eliminating the need to process the raw data each time.
That's right.
That sounds like a huge time saver.
Data cubes represent multidimensional aggregates,
Okay.
allowing you to quickly slice and dice data along different dimensions without having to perform expensive calculations on the fly.
It's like having a pre-built spreadsheet with all the answers you need,
Exactly.
ready for instant access.
That's a great analogy.
It's like having a cheat sheet for common calculations.
Yeah.
You've already done the hard work, so the answers are readily available.
What about materialized views?
Okay, yeah, what about materialized views?
How do they differ from data cubes?
Right.
Materialized views are another way to pre-compute query results and store them for fast retrieval.
Okay.
They act as virtual tables that represent the result of a specific query.
Right.
For example, if you frequently join data from multiple tables to get a consolidated view of customer orders,
Mm-hmm.
you could create a materialized view that represents this join.
Gotcha.
When you query the materialized view,
Okay.
it's like accessing a pre-joined table,
Right.
eliminating the need to perform the join operation each time.
So it's like having a shortcut
Yeah.
that bypasses the complex steps of joining multiple tables. You're essentially creating a pre-assembled puzzle ready to be viewed
But wait,
without having to put the pieces together every time.
that's a great way to put it. Materialized views are powerful tools for optimizing query performance,
Okay.
especially for complex queries that are run frequently.
Data cubes and materialized views, two powerful tools in the analyst's arsenal
They are.
for getting quick answers from massive data sets.
Absolutely.
Wow, this deep dive into storage engines has been incredibly enlightening.
It has.
We've journeyed from the simplest key value stores to the sophisticated structures that power modern databases.
We have.
And we've even explored how different workloads demand different approaches.
Yeah.
What are your key takeaways from all of this?
For me, the key takeaway is that databases are incredibly complex and fascinating systems. They've evolved over decades to efficiently manage and retrieve vast amounts of information,
Right.
employing a variety of ingenious techniques
Yeah.
to optimize performance and ensure data integrity.
It's really amazing.
Understanding these underlying mechanisms empowers you to choose the right database technology for your needs,
Right.
design your systems effectively, and unlock the true potential of your data.
Well said. It's not just about memorizing facts.
Yeah.
It's about gaining a deeper understanding of how things work.
Right.
So you can make informed decisions,
Yeah?
troubleshoot issues effectively, and
Yeah.
ultimately become a more proficient data professional.
Absolutely.
This knowledge is invaluable in today's data-driven world.
And as data continues to grow at an exponential pace,
Yeah.
it's exciting to think about the innovations that lie ahead. New storage technologies, more efficient indexing algorithms,
Right.
and even quantum computing could revolutionize how we handle information in the future.
That's really cool to think about.
It's a dynamic and ever-evolving field,
Yeah,
and there's always more to learn and explore.
absolutely. It's a journey of continuous learning and discovery.
It is.
Thanks for joining us on this deep dive into the world of database storage engines.
It's been a pleasure.